In this session, we're going to start looking at dynamic data. All the data we've been using up to this point has been considered static data. That means once it's declared, it stays the same. The value can change, but where it is located in memory, how big it is, all stays exactly the same. So that's because it's allocated at compile time. In some cases, it's a much less efficient use of memory. For arrays, for example, we know that we have to overestimate how many values we might store in there, particularly if the user's involved or we're reading data from a file. And the other thing about it is that if we've had to reserve this big array, for example, it exists for the whole time that the program is running, or the whole scope. The nice thing about it, though, is that it's very easy to use. So whenever we're learning to program, we'll always start with static data. But as we start to become more experienced programmers, we realize that it's not very efficient to declare, to overestimate how many things we have to have in an array. But just as things come in, let's reserve memory for them at that point in time. So it's allocated during actual code execution time. So it very efficiently uses the memory that we have. We add elements as we need them, and if we don't need them anymore, we free up that space to allow it for other variable declarations. The only problem is it takes a little bit more time to learn how to use these, but I think once you've started using them, you'll realize the value and want to keep using them. So before we start talking about how to do dynamic memory allocation, let's talk a little bit about what happens in memory overall. So we have two different areas. We have a stack and we have a heap. The stack is going to start at a particular address and go down in memory locations, where a heap is going to start at a low address and work up in memory. Generally, these are in the same space in RAM. And so they're going to be sharing space. And if, for some reason, we start getting into that center part, we could have memory problems. Now, static memory is generally going to go into the stack. So if we call a function, for example, those parameters are going to be passed on the stack. Dynamic memory is going to be allocated in the heap. So we have some variables being stored here. We have some, if they're declared dynamically, being stored here. Normally, we don't have any real issues with this center part of memory interfering with each other, so the stack coming down, the heap going up. Generally, we don't have problems, but occasionally we will, and we'll talk about a few of those as we go through this section. ANSI C has four basic dynamic memory allocation functions, the first of which is malloc. So the M stands for memory, the alloc stands for allocate, and what it does is it reserves a block of memory for us, and contiguous means they're all in a row or sequential. So we're going to get a block, however big our request is, of memory locations of a certain data type, and it's going to return to us a pointer to those. So the function is malloc, it returns a pointer, or if for some reason the allocate didn't work, it's going to return null. What it expects as a parameter is the total number of bytes that we need reserved. So if we say 5 integers, it's going to reserve 1, 2, 3, 4, 5 spots for us to hold integer values. So let's take a look down here. What we need to do is to say, there's our function, malloc, and we want to pass in the number of values we want times the size of an integer. So because this data type is system dependent, we need to say the size of an integer on this platform is 2 bytes or 4 bytes or 8 bytes, whatever it happens to be, multiplied by how many of them. So if I want 5, this is going to reserve enough space to hold 5 integers. Here we have some typecasting. And what that means is we're going to force the returned value from this function to be a pointer to an integer. That's called iPointer. That typecasting is necessary to use with malloc. So at this point, assuming our allocate was successful, we now have iPointer that is pointing to the first location in that block of memory. Calloc is the second of our dynamic memory allocation functions. The C stands for clear. So with a malloc, it reserves that block of memory, but it leaves them with whatever garbage happened to be in them when it started. So calloc will actually clear that block for you. So same thing, we have a continuous block of memory, so we're going to get that block. But this time, whenever it's finished, all of them will be initialized to 0. So the format is basically the same. We're returning a pointer. Calloc is our function name. Here, though, we have two separate variables. So the first one we can see down here in our example is the number of values, so that was the 5 we used before. And here, in this time, we're using floating point numbers, so this is going to tell us how big or how many bytes one floating value takes. So here we have two separate values, the number and the size. Again, we have our typecasting that forces it to a pointer to a floating number, and there's the value. Now, if after this instruction has executed, f pointer is null, that means there wasn't enough space for us to reserve this block. If it is, then f pointer, it was successful. In other words, f pointer isn't null. It's going to be pointing to that block of cleared floating point values. The third of our dynamic memory allocation functions is free. And this is the one that lets us say, I don't need that memory anymore, I'm finished with it, and it releases that allocated memory back to the system, and so it can be used for something else. The format is pretty simple. The function name is free, we give it the pointer, and it doesn't return anything. So if we look down here, here's an example. So here's our function call. Here we're passing in the pointer to our integer block that we declared with malloc, or we could have passed in f pointer, which was the pointer to our floating point block. So all we need to know is the name of the block that we want to free up, and it's going to release that memory back to the system. The last of our dynamic memory allocation functions is a pretty powerful one, and this one is called reallocate. What it's going to do is it's going to, just like malloc and calloc, reserve a block of contiguous memory, but what it does is it allows us to grow things. So this is where the problem we had with arrays before, when we had to over reserve. Now we say we have one array element, oh now we've got 2, oh now we've got 3, and what it's going to do is it's going to keep what we had before and add new things onto the end. So the function is reallocate. Here again we're going to need to typecast to return a pointer. So this is going to be the address of that reserved block, or null if there was a problem. And here, like calloc, like malloc, we're going to pass in the total size. But we also need one more thing here, and this is the pointer to an existing block. So we had a block that had 3 elements in it. We're going to pass the pointer that we had here into there and say, give me 5 blocks, and it's going to add 2 more onto the end. Then if we pass that pointer in again with a reallocate and say, now I need 7, it's going to add 2 more on the end. So it's very important that we remember this is the total size. Let's take a look at an example down here. There's our function reallocate. Total number of values times the size of each one. So this is like malloc. It needs a multiplication in there. We need to typecast to the type of pointer we have, and iPointer, assuming the reallocate is successful, is going to return a pointer to the new block, or it's going to return a null. Now the thing we have to remember with reallocate is that if we had those initial 3 spaces reserved for our data, and we do a reallocate, and it now needs space for 5, Sometimes it's going to move that in memory. If there isn't enough space where the original block of 3 was, it will grab the whole thing and move it to a new space in memory. Once we've declared our dynamic memory, we then have to be able to use it, and this is where pointers come into place. So what we're going to do is use the contents of or indirection operator, which was our star, to get at the space in the memory that's been allocated for us. So here we can see something we've seen before. We have I pointer, which is our pointer, plus the offset into the block, and we're saying the contents of. So here we're going to assign value into that block. So maybe our pointer is here and we've set an offset of 2 elements, so in here we're going to write value. The second one, we're going to do a scanf, and we're expecting an integer, and here I pointer, remember, is already an address, plus our offset gives us a new address, so we don't need the ampersand when we're working with dynamic memory here. So we're going to read a value and it's going to get stored. If our index was 4 now, it's going to get stored in here, whatever the user enters. And if we look at the last one, here's where we're going to output what's there. So we're going to start with an index. We know that there are a number of elements in there, and we're going to print each one. So we're starting with the first one, I pointer plus 0, the contents of that one. We'll print here. We'll increment I will now be 1, so we'll print I pointer plus 1, now gets us this one, we print that, and so on through our block of memory locations.